Our next speaker is the head of the Research Center Cognitive Computing in Life Science at THW. She got a Business Insider Future Marker Award and was listed Woman Under 30 in Robotics You Need to Know About by Robot Hub. She leads the neuromorphic computing group that developed brain-inspired sensing and processes technologies to enable assistive robots with applications in health and elderly care. She has a degree in physics and a doctoral in neurocomputation. Let's welcome Yulia Sandamirskaya to the stage.
Thank you. Thank you so much for the invitation. It's a real pleasure to be here. Mind-blowing talk just before me. We'll have to make quite a step from the deepest depths of the matter on this planet back on the surface of the planet in more daily life and business in our homes even. So I will talk about robotics and the intersection between robotics and AI and the challenges there. I will skip this first slide because this question, why do we build artificial intelligence systems, I suggest that we discuss it in the coffee break. But in short, smart people were, through history, very interested to understand how their smartness works, and they had their understanding of what it means to be smart, playing chess, playing games, talking, writing emails. And then they try to build useful technology based on that, right? But there are a lot of things that don't look so smart, but are actually very difficult for artificial system to solve. All this hard work, moving things around, doing some repetitive work. It would be really nice to have some help there from artificial systems. Although for some of us, having an assisting system at home might be just nice to have, right? We can manage this stuff, but there are some people who really need assistance in their daily life. If you have a disability, or as you get to an older age, life gets really difficult. Small things that used to be easy become hard, and you start have to rely on other people. And it's nice to be around people, but to have to rely on their help is really difficult and annoying. The cost of long-term care in Switzerland is really high. The estimated 3 billion per year is what people spend on helping elderly and people with disabilities. And a lot of that help is small little tasks, which you would think would be easy to solve with the robotic system. So where do we stand today in robotics? I don't know if you follow the news, but we live in exciting times. There's an explosion of robotic systems out there. Alone in China, there are 200 startups working on humanoid robots, and there are dozens and dozens across the world. Why humanoid embodiment, one could argue, but it's an amazing embodiment. It means that we can build robots that mechanically have similar complexity to our own. We can build robots that, in principle, mechanically can do everything we can do. Whether they need to be humanoids or not, so the question is, today's environment are built for humans, so maybe if the robot has similar embodiment, can do similar things, it will be easier to adapt to our today's environment. But the contra would be it's a very complex robot, it's an expensive robot, it might be difficult to control it, so there's a debate. But the message is mechanically, we can build whatever we want. Now, I don't know how many of you had the pleasure to interact with one of these systems. We had some humanoids here in Switzerland, for instance, this Chinese humanoid Unitree. So I wanted to see how intelligent it is. Everyone around me was very excited. Oh, have you seen it, have you seen it? And it can do two things. It can walk around, approximately like this, and it can shake hands. So I said, okay, shake hands. I want to try this functionality. It's not trivial to shake a hand. So this is how it looked like. Let's see if the movie will play. You see it? You see the dominance? I have to move my hand to the hand of the robot. Why is it so? Why doesn't it move towards my hand? Would it be able to grasp and bring me anything, any object, to go towards any object? Can it learn new stuff? Can I show it my phone or my favorite cup and say, hey, this is my favorite cup, bring it to me, full of water? Is it safe? And of course, in order to be all that, it's not enough just to have the body that looks like human. We need intelligence that is somewhat like humans do. Okay, so artificial intelligence today, I think in this room everyone knows what that is. It's all started with image processing, still does a lot of image processing today. Text processing is another thing we can do these days. Let's look under the hood, but not for too long because I assume all of you are experts here, right? So what is artificial intelligence today are artificial neural networks, and why are they so powerful? What makes them so powerful? So what you do, you take a fairly simple model mathematically, right? So it's a relatively simple algorithm. You add a lot of data, really a lot of data, and it's important that your data covers all the corner cases. So it kind of covers all the space of what could go right or wrong, and a lot of compute. And then there's a little bag of tricks, right? So how you train these networks so that they don't forget, you don't have catastrophic forgetting, and that learning converges. But in the end, you have the network. It does all these amazing things that the deep networks do today. It comes at some cost, right? Training it costs a lot if it's a large network. There are a couple other kind of warning signs. I just list them here. I guess you're aware of them. The first one is transparency. So if you have trained your big, large network, it solves your task, but you don't know exactly why and how. And if it makes a mistake, you cannot really attribute why exactly this mistake happened. Robustness is similar. So in the old time, there were these funny adversarial examples showing that you have your network, it can recognize animals, let's say, and it tells you this is some certain monkey. And then I can train another network. It will generate an image of the same monkey, just a few pixels are changed, and the network will say, no, it's an elephant, or it's a gibbon, it's something else, with 99.99% of confidence. So there are these worrying signs. If the network solves your problem, it's difficult to see how exactly it is solved in its deep structure. And the third challenge is adaptivity. So if I discover, when I had my data set, I forgot one important type of a corner case, I want to add it now. It's not so easy to just add new information. You usually have to retrain. And retraining is difficult. You cannot just train only on this data. You often have to revoke all data. So the question, can we use this method for robotics? If you ask 90% of roboticists and AI people today, say, yes, let's do that. Let's only do that. Let's forget everything else we've done in the robotics. And yes, so there's some success in using these trained networks in robotics. Typically, they will be trained in the RL, reinforcement learning paradigm. And a couple successful examples actually come from Zurich. One from the University of Zurich, David Escaramuza's lab. So he has shown for his drones, the flying robots, that you can train policies that allow these drones to fly at a very high speed in a very complex environment like in the forest. Trained completely end-to-end in simulation. And the second example is from ETH of Zurich, Marco Hutter's lab. They have a quadruped robot, the dog, animal it's called. And they have also shown that in an end-to-end fashion with reinforcement learning in simulation, you can train this robot to do sophisticated tasks and skills. However, for more complex behaviors, and what do you mean by more complex? So both drone flying and robot walking is relatively simple. It's just about moving around, and I say just. So the only thing you need to know where things are, where potential objects are. So 3D voxel grid of your environment is enough. So you need a relatively simple perception. And then the rest is just controlling the body with proximal. If I have some sophisticated robot that in my home needs to find a glass, a discrete object, recognize it, localize it, grasp it, and bring it to me, the complexity of the task is much, much higher. And you can see some impressive videos how the things like that were trained, but you can also find some impressive fails videos, at least from honest labs like the Stanford lab. They have no problem showing you the outtakes for the fails. Yeah, pressing Control-C, they're always fun to watch, and there are always plenty of them. One example that I liked in one of these video sequences is that the robot was pushing five chairs to a table. And it did all 5 of them, and the comment was, but it was trained only with 3 of these chairs. And the chairs are exactly the same, but they were proud that it worked for the chair number 4 and 5. Yeah, so what are the limitations of these models for robotics? Why is it so challenging to apply them to robotics? So first, the models are typically trained for one task at a time, but the robot might need to do several things at a time. And you need a much more multimodal approach. So it's not just about images and text. Today, if people say multimodal, they mean you can take text and also images. And it happens to be exactly the thing that's out there on the internet in large quantities. On the robot, you have other sensors. You have motor sensors, you have touch sensor in the skin, you have different types of visual sensors, you have depth cameras, you have color cameras, you have some funny cameras that detect only change of luminance in the environment. These different sensors have different sampling rates. So they're not all run at 30 frames per second. Some of them run very fast, quickly, like LiDAR, and delivers maybe a very small amount of information. Others deliver you large images very slowly. So they have different image analysis. They have different reliability. Some you can trust more, others less. And they can have different and changing geometrical arrangements. So if I have my, I can say, OK, that's all fine. I will just record the data set with all the sensors. I'll take it all into account. But in my data set, one camera will be here, another one there. I train my model, it works well. And then for some reason, I decide, you know what, I want to move the camera here, or maybe there. So kind of the relation between the cameras changes, and I, strictly speaking, need to re-record my data set, because now the meaning of the data when I move is completely different. Now, let's assume, OK, you know what? I will train an individual model for every modality, like one for skin, and one for motor, and one for eyes, and for different behaviors. And I will have just a lot of these agents. They solve different tasks. But then orchestrating all these different agents, that becomes the major challenge. Right, so that becomes actually the problem. How do I decide when to pay attention to what and when to engage in which behaviors? That's then the big question that still needs to be solved. Then these models tend to be data hungry, and robotics, as any physical system, is not so data rich. It's hard to collect the data. And moreover, the physical world is fundamentally complex and dynamic. New things appear. The language, the life language. I have teenage kids. They come up with new words and phrases and memes and references every week. New objects appear. Things change in quite a substantial way. And the complexity is immense of the world. So if you would like to put it all in the data, and this is what people try to do these days, I would claim that's impossible. High latency is also a problem here. We don't need to go to nanoseconds in robotics, but milliseconds would be good. So large models are still too slow for us, and going somewhere on the server is still too slow for us. So there are some overlaps here. Yep, so our control needs less than 1 millisecond, ideally like around 1 millisecond latency. Yeah, and accuracy and robustness is also very important. We forgive ChatGPT if it forgets a word and gives us mistake 20% of the time. If it's an elderly person, if my grandma is taken care of by the robot, I cannot forgive 20% mistakes there. It needs to be reliable. Yeah. So a little excourse, how did we get there? So I think that we are kind of at the wall because so much has been invested and the tools are so seductively easy. It's much easier to do this deep learning than anything else. And how do we get there? Is a brief history of computing, right? It all started with the Turing machine, this suggestion that we can compute anything with this type of a device. People built the device, and the rest can be captured by a single word, scaling, right? And then we just put it on steroids and build bigger and bigger computers. And there was the Moore's law that told us the computers get faster every couple of years. So don't worry, we'll get hardware that can solve any of your problems. We got to a PC, and it all was fine until it was not enough. And when was it not enough? I think this room might be not so obvious. In some other rooms, it's like when the gaming became so popular, they figured out the CPU, so the Turing machine-like compute, was not enough to render nice 3D pictures on the screen. So what happened then? It needed faster rendering, and then graphical processing unit was invented that allowed you to parallel process the pixel information to draw nice 3D pictures. And then NVIDIA was clever because they not only developed this hardware parallel, but they also developed a software and partially open sourced it, allowing the people to experiment with it. You don't have to only do graphics, you can also do other stuff, like neural networks. They happen to match very nicely this hardware, and people could play around with them. And yeah, so that's why today we are where we are. So the success of today's AI relies on this hardware kind of co-design, or match between the hardware and particular type of neural networks. So if you go on the market today, there are like 2 computing systems, basically, a CPU and a GPU, and maybe FPGA, and everything else you have to design yourself. So is there anything else? Now for robotics, now I just do a very brief excourse. So if you think about all those tasks that the robots need to solve, they need to move around, they need to detect objects, they need to maybe grasp this object and bring them somewhere. We have examples from nature that solve these tasks with amazing efficiency. There's a little fly up there. It has a brain with 100,000 neurons, that's it. And it can fly around, it can distinguish different smells and visual patterns and can do amazing things. And then the birds, the brains, so the brains are just extremely efficient, also using some kind of neural networks. And they're adaptive and flexible and fast, can be very precise and very efficient. While dealing with real-world complexity, learning new tasks can be cognitive. I won't go into detail, but people say, yes, but the brain is so complex. We'll never understand what they're doing. The complexity is immense, but today we actually know a lot about how the brain works. And the main thing that we know are two things. First, that there are not just one, but many different algorithms working in the brain. We have a lot of different intricate structures that are responsible for different parts of our behavior, like, for instance, attention, that we filter out what is important and what is not important. There's a particular circuit that does it. And then many, many others, hundreds of different circuits. And the second thing that we learn is that these circuits continuously change. They're not just trained once and then stop. The connectivity matrix, the weights, they constantly change. It's a dynamics that's not only running in activation functions, but also in the connectivity. So, there are people who model all this stuff, and there are a lot of models and algorithms ready for us to use. So why don't we just use them? And that's because they don't run very efficiently on either CPU or GPU. Why don't they run efficiently on the GPU? These are massively parallel algorithms, but they are not images or matrices. And the GPU works well with everything that looks like an image or a matrix, like a vector, dense vector. If it's something sparse, something graph-like, then it gets more tricky. We have sparse neural networks, and we have a lot of recurrent neural networks. We might use different transfer functions, so not just very kind of simple and optimized ReLU functions. Our synapses might need to change, so the weights are not constant, all weights change. And we might need asynchronous processing, because different parts of the architecture might run at different rate, with different speed. So that's why, over the last decades, people are thinking of another type of hardware, specifically for solving these tasks of real-time control. They named it neuromorphic computing hardware, from neuron-like, brain-like, brain-inspired neuromorphic hardware. So I won't go into detail, but there are different types of these neural chips. Some of them are analog, so they use analog electronics to mimic the dynamics of biological neurons. Others don't. Others use normal digital electronics. Some people use novel materials. They call them memristors, that allow to make these chips very compact and very efficient. But in short, it's a massively parallel system, similar to a GPU, asynchronous, and with less constraint on how your connectivity matrix should look like. Intel has one chip like that. It's called Loihi. They made an effort to compare it with other systems, and these are some numbers that they got. So if you look at this corner there with recurrent networks, then their chip was 100,000 times more energy efficient than similar workload running on a GPU or some other accelerators, and at the same time, 1,000 times faster. So there are orders of magnitude efficiency and speed that you can win by using this hardware. There are a lot of neuromorphic chips on the research market, and the big question now that we have them, so how to program them? Because we cannot always use TensorFlow or Keras to program them. But there are examples how people program them. I won't go into detail, just flash them briefly. So one way to program them is just get inspired by biology, take those biological circuits, and implement them on these chips. And people have shown that you can get very efficient systems for controlling little drones or vehicles. Yeah, so in my lab, what we do is that we take these computing chips, we take the sensors that are also inspired by our sensors, by the retina in the eye, by the cochlea. We build models, cognitive models, that solve different tasks, all the way down to control. We put it all on the robot and try to get from robots that can only navigate in human-centered environments, and that is solved basically, right? We all have, or many of us have vacuum cleaners at home, to go to robots that can also manipulate discrete objects, that have arms and grippers and can grasp and manipulate or transport objects. All right, and this is our team in Castle of Wädenswil, where we work on this technology and try to bring robotics to the next stage. Thank you.
Thank you very much for the talk. I'm very much looking forward for the day that I have a robot to clean my room and make my bed and everything. That would be great. That'd be fantastic. Okay, so now it's we're taking questions. Let me see if there's anything from the app. But if anyone has a question in the audience, we will take it from you first. There you go. We have one from Tia.
Thanks a lot for this really cool talk. Do you have some examples of kind of a neuromorphic system running in a robot, and roughly maybe a latency power comparison to more conventional?
Mm-hmm. So the Intel had these latency power comparisons, and they are 5 orders of magnitude faster. So the chip itself can be much, much faster. The bottleneck to run it on a robot is usually in the interface. So all the chip designers, they get excited about the chip and they forget that we have to also stream the data in and out. We insist on the latency below 5 milliseconds for robots, and maybe the most kind of impressive workload was in model predictive control. You have to solve a pretty substantial optimization problem with 2,000 variables, and you have to solve it within 4 milliseconds. So that was maybe the fastest large task that we've solved with this latency. And the power consumption was 1,000 times less than on a CPU. The same problem, also optimized to the top of it.
And with because an FPGA can also kind of mimic an event-based system, is this comparisons also done with other more low power?
Right, so usually FPGA would be much higher on the power side. It can be as fast. So in that sense, yes, it would probably take more space in terms of the device size. Yeah, interestingly, one of the key figures in this field, Karl-Heinz Meyer, he actually came from CERN. So he was working on detectors for particles and then got inspired, and one of the chips, it's mixed signal, analog digital, is inspired by the tasks that you have in CERN. Yeah, there's an interesting connection.
Thank you very much. I see there is questions coming in the app, but unfortunately I was told that we don't have time for more questions. So if you have any more questions, maybe take the break. It's lunch right after the session, so feel free to have a chat.
Thank you.
Thank you very much for your